In this video, I will present a proof of the arithmetic and geometric mean inequality using the second law of thermodynamics. Let's first unpack what these words mean, starting with the inequality. The arithmetic and geometric mean inequality, or Amgm inequality for short, looks like this. It's a statement about lists of numbers, for example, 3, 1, 4, 1, 5. The term on the left-hand side asks you to sum all the numbers in the list, and then divide by the number of numbers. This is the average you're probably already familiar with. The so-called geometric mean is on the right-hand side. It asks you to take the product of all the numbers in the list, and then raise that answer to the power of 1 over the total amount of numbers. The Amgm inequality then states that the number we get from the first process must always be greater than the number we get from the second process. And this works for any list of numbers. So it would appear that the inequality holds for all our examples, but of course in math we have to know for sure. And that means coming up with a proof. This is where the second law of thermodynamics comes in. But before we can discuss it, we first have to make a fast detour to explain the concepts of heat, heat capacity, and entropy. I'll do this with the help of the example of a solid block. The definition of heat, Q, is thermal energy in transit. So, as we raise temperature, heat flows into the block. And as we lower temperature, heat flows out of the block. For most solids, the change in heat is directly proportional to the change in temperature. We define the proportionality constant to be the heat capacity. So that's heat and heat capacity. What's entropy then? Entropy is a measure of microscopical disorder. The change in entropy is calculated by adding up all the small changes in heat over temperature. That is, taking the integral of dq over dt. But we already know the change in heat for a block. That was just c dt. Integrating this between an initial temperature Ti and a final temperature Tf then gives the following equation. Delta S equals C times the ln of Tf over Ti. We'll need this equation later, so let's dagger it. One of the fundamental laws of nature can actually be expressed in terms of entropy. The second law of thermodynamics states that the total entropy of the universe must always increase. So, anything you do will always result in a net increase in entropy. Much like a room that, if left uncleaned, only becomes more disorderly. Interestingly, many physicists believe that this defines the arrow of time. This one law ensures that time must always flow forwards. Okay, let's now finally get to the proof I promised. The second law implies the Amgm inequality. So this fundamental law that dictates the flow of time itself also implies this important result in math. And here's how it works. Let's build to the full setup for the proof by considering a simpler setup first. Let's consider two blocks, one at 0 Kelvin and one at 100 Kelvin. Let's now push them together. From physical intuition, we know that the temperature must average out to 50 Kelvin. Note that the arithmetic mean pops up naturally here, so let's try and generalize this. Consider n different blocks, all of different temperatures labeled Ti, where I tells you the number of the block we're considering. By the way, only 9 are drawn right now, but we'd like to consider an arbitrary number of blocks. Let's push them all together to create one big block. As before, the temperature will simply average out to the mean temperature. To be precise, the arithmetic mean temperature. Here, Tf is the final temperature. We'll also need this equation later, so let's double dagger it. Let's now look at the change in entropy for each individual block. Recalling our daggered equation, we know that the change in entropy for a single block is C ln of Tf over Ti. For simplicity's sake, I'm gonna set the heat capacity equal to 1. The second law is a statement about the total change in entropy. so we need to add up all the individual changes in entropy. Plugging in the formula we found earlier gives this long sum of logarithms. Recall the log laws. The sum of logs is the log of the product of their arguments. So this expression actually equals the log of the product of all the final temperatures over the product of all the initial temperatures. Recognizing the numerator to be Tf to the power n then gives the following expression. Let's now invoke the second law of thermodynamics. The change in entropy must always be positive, so the Ln must always be positive. But a logarithm is only positive if its argument is greater than 1. We therefore get the following inequality. We're almost there. Rearranging and then taking the nth square root gives this. If we now plug in the result found earlier for Tf in the double-daggered equation, we end up with the Amgm inequality. So not only does the second law of thermodynamics determine the arrow of time, it also proves this amazing result about averages. As a final thought, I would like to leave you with a question. In the video, I set the heat capacity equal to unity for the proof. What happens if we don't do that? Do we perhaps obtain a stronger statement about averages? I hope you enjoyed this video. Please consider liking and subscribing if you did. Thank you for watching.